We have already studied the effects of force on a body in the previous class, haven't we? Students, now let us organize these to review the various effects of force. First, force and motion. Students, force changes the state of rest or motion of a body. Here is an activity to prove it. Keep a tennis ball on a table and push the ball slightly with your hand. What happens to the ball? The ball at once sets into motion, isn't it? Now, keep your hand on the opposite side of the moving ball. What happens then? The moving ball comes into a state of rest. This proves that the force changes the state of rest and even the motion of a body. Students, force can change the shape of an object. The change produced by a force on a body cannot be observed clearly. Look at this activity. Do you have an eraser? Take an eraser. Then, insert 2 nails, each of 1 inch, at the near ends of the eraser. What change do you observe in the eraser? You will observe both the ends of the eraser near the nails slightly increase. Similarly, when a spring is stretched holding it in between 2 hands, the shape of the spring will be changed. Students, force can change the direction of an object as well. To prove this, look at the activity. Do you have a toy car? Or a bus? Or even a motorcycle? Take a toy car, or a bus, or a motorbike, and tie a thread in the middle of one side of a spring around the car. Allow the toy car to move on the floor. It moves straight when it is in motion. Now, pull the spring towards you, as in the figure. Does the direction of motion of the car change? It does. Similarly, when a football player strikes the moving ball in another direction, the ball changes its direction.
In balanced and unbalanced forces. Newton's first law of motion states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. But how are balanced and unbalanced forces different? Balanced forces will cause no change in the speed of an object. Balanced forces acting on an object in opposite directions and in equal strength, as shown in the arrows below, do not cause a change in the speed of a moving object. Objects that are not moving will not start moving if acted on by balanced forces. Remember, forces have a magnitude and a direction. Unbalanced forces are not equal, and they cause the motion of an object to change. When 2 unbalanced forces are exerted in opposite directions, their combined force is equal to the difference between the 2 forces. The magnitude and direction of the net force affects the resulting motion. This combined force is exerted in the direction of the larger force. Let's take a look at some real-world examples. The forces acting on the red pool balls are balanced. The downward force of gravity is equal to the resistance force of the pool table. When the white ball strikes the red balls, the forces are now unbalanced and they move in the direction of the force. The forces are balanced on the weights. The downward force of gravity is equal to the resistance force of the yellow rack. The weights do not move. The weightlifter exerts an unbalanced force upward, and the weights move in that direction. The forces on the tennis balls are equal. They are not moving. When the tennis balls are struck by an unbalanced force, it causes them to move. The resistance force of the car is balanced with the downward force of gravity. The car jack exerts an unbalanced force on the car upward, and the car moves in that direction. The car is at rest, and all forces are balanced. When the car that is moving strikes the car at rest, then the forces now are unbalanced, and the car moves in the direction of this force.
Momentum is inertia in motion. A lot of momentum means a lot of oomph. An even better way to describe momentum is as the product of mass times velocity. This means that if something is moving, there are two ways to affect its momentum. One, there's the mass. You know, for the same speed, a massive truck has so much more momentum than a mosquito. And two, look at the velocity. A baseball thrown gently by a kid will be easy to catch. That same baseball, thrown at 100 miles per hour, might knock you over. So a tiny bullet at a high speed has a lot of momentum. Wear a bullet vest and it'll still knock you over. An oil tanker creeping along at only a few miles per hour also has a lot of momentum, not by virtue of its speed, but by virtue of its great mass. Because it has so much momentum, so much inertia in motion, the tanker can't just pull into the dock. Rather, it's greeted by powerful tugboats that help to manage its maneuvering. A fast-flying tiny bullet and a creeping massive oil tanker are both difficult to stop. Both have a lot of oomph. That is, a lot of inertia in motion, which you now know to be what we call momentum.